So as you can notice in the program, this is a teamwork we will present today. But contrary to what is indicated in the program, we will speak in English, not in French, so I will present him in English. So Raphael Marée received the PhD degree in computer science in 2005 from this university. After a postdoc at Pasteur Institute in Paris, he is now working at ULiège, where he's senior researcher and scientific coordinator of the CESERH project since 2010. His current research interests are in the broad area of machine deep learning techniques with specific focus on their application to various problems that involve very large sets of high-resolution images. He is also currently member of the management committee of the EU COST Neubias and Comubis networks and co-lead of their software development work packages. So,
thank you very much. So, should I say good afternoon or good evening? I don't know, but whatever. I will so present the cytomine research project that I'm indeed coordinating since 2010. And since it was primarily motivated by biomedical application, I will illustrate in the first part of this talk biomedical application of these techniques and software, but then I will include more recent work that is led by Pierre Goers and done by Mathias Sabatelli in the field of works of art. And so where we reuse this software to solve different problems. So just to briefly mention that I'm part of the Montefiore Institute, which is the Department of Electrical Engineering and Computer Science here at the university. We are located up the hill in the forest, and there I'm collaborating with these professors in machine learning. But in general, when there are projects that involve image analysis, I'm most often in the loop, and so that's why today I will show you several projects involving image analysis done by several colleagues and myself. So the project that I'm coordinating started in 2010 when I started to work with biomedical researchers, and I quickly realized that these people are generating and analyzing a lot of imaging data. They are using various instruments to analyze human samples, but also animal models. And so what you see here is different flavors of images that are generated by these different instruments. But more specifically, I started to work in the field of digital pathology, which involved the acquisition of tissue samples. So what you get is here an organ of a human or an animal models that are prepared according to several steps that basically end up with this glass slide, which is like 7 centimeters long and 2 centimeter width. And then these glass slides go through what we call slide scanners that generate very high resolution images. That means that these images can have 100,000 pixels by 100,000 pixels, for example, and these can be generated very fastly in a few minutes. And so what I realized then is that these people working with this type of equipment and technologies are indeed analyzing very diverse types of images. And so these two next slides are only a very small subset of examples of forms and patterns that they analyze. Here it's in the field of cytology, which gave the name to cytomine, which basically is the analysis of cells. And so what you see there is different types of cells according to their shapes, to their colors, etc. That they usually have to recognize and to detect and quantify in the samples. But we also work it, for example, with people in the development field, where these guys are analyzing zebrafish examples. And so again, you see that all these images are related to zebrafish, but they have been acquired using multiple instruments. And so there is a large variety of images that we have to analyze in this field, and so that motivated the development of generic tools, because it's not possible for each of these problems to develop a specific tool, so we started to work on the development of a generic tool. And even when we started to develop this tool, we already had in mind to apply it to other fields beyond biology. What is important to understand is that in this field they are not, of course, only looking at images. They want to analyze these images, they want to measure different types of cells and tissues, they want to quantify the number of cells, they want to quantify the distances between different types of tissues, etc. But what we realized is that at that time they were very often performing these tasks manually or semi-manually. Because of that, because they had a lot of data but only manual tools, they are often only using subsets of their data. And very often also these studies are performed by isolated experts. So when they analyze this data, they only do it in their own lab, and then the data stays on hard disk, etc., but are not shared. And so this is a waste of resources, we believed. And also what we realized is that they are using proprietary softwares, which means that it's not easy to reuse their analysis, their results from one software to another. So we finally decided to develop from scratch a new tool, including different libraries that were existing, but we designed a whole software that we published 6 years later. And this software is fully open source. That means that you can reuse it, inspect it, and read let's say the recipe of this software, so that you can understand how it works, and you can adapt it to your own application. Basically, what this software enables is to work collaboratively through the internet. And so this is a very simple overview of the features of the software, where you can imagine that you have the following workflow. So people generate images. They can upload their images to a server through a web browser. And once they have uploaded these images to the server, they are accessible to their collaborators. And so they can zoom in and zoom out in these images. And you can have multiple experts accessing these images. So you can ask several, in the biomedical field, you can ask several biologists to analyze their images, and they all have their own layers of annotations. But the idea, of course, is to ease the analysis of these images. So the idea is that to use this knowledge of these experts to train machine learning or deep learning models. So in this workflow, where the goal is to quantify some type of tumors in these images, we ask first experts to analyze, to manually annotate some region of interest, and then we use this manual annotation to train machine learning models. And the idea is that these machine learning models, although we are computer scientists, we do not trust them all the time, so we provide proofreading tools in the web interface, so that these experts can analyze the prediction done by this machine learning algorithm and correct them if they are not correct. So this is basically illustrated here on tissues, but this can be applied on other image data, of course, and I will show you examples later. So I will very briefly describe some of the features of the software, and then I will show application of machine learning on biomedical data and works of art also. So the software allows you to organize your data on the web, and so what you see is each of the boxes here correspond to one project. So you can imagine there to put some type of images, like tissue of a given animal models, but you can imagine that this box is related to works of art images, and this box to other types of images. And you can give access to these different boxes, different projects, and so you control which collaborator have access to what kind of data. The tool allows you to visualize these very large images. And so you can, like Google Maps or OpenStreetMap, you can zoom in and zoom out in these images. But in addition, you can, we provide tools to annotate these images semantically. So the idea here is to allow experts to draw contours of region of interest like tumors or the different types of tissues according to what we call an ontology. So on the website it's possible to define an ontology, so it's a vocabulary of terms that allows experts to describe these different objects in their images. And so the experts can build atlases of different kinds of objects that they have in their images. And then what we allow is to basically extract in both ways, so importation and exportation of data, so that you can plug machine learning algorithm or image analysis algorithm. So basically the software is very interoperable, so you can plug your own algorithms. If you are a computer scientist developing tools, you can use our interfaces to test your algorithm on the data. And so that's basically what we did for several projects since 2010. And so what you see here is several, only a subset of application of the tool on diverse types of data. So you have examples of in biomedical domain, but also here these are images of the moon where the goal is to detect craters in these very large images, or here you have satellite images where the goal is to detect forest, to study deforestation, etc. So now I will show you several applications of the tool and of this algorithm, and I divided these examples in 4 categories, because in fact in computer vision there is not only the field of visual similarity computation, but there are different tasks that you can solve with different types of methods. And so I will show you 4 tasks. The first one is what we call segmentation. And in this task, here you have an example of segmentation task where the goal is to detect these regions which actually are tumors. And so with these people we worked on a large set of images. They have thousands of images to analyze. But up to now they were doing the job manually, so they spend a lot of time because these images are very large and you can have several hundreds of tumor isolated in each image. So for example, these are examples of image they had to analyze before. And so what we propose them is a hybrid human-computer approach, where the first step is to ask as I previously explained, to ask the expert to manually annotate examples. So that's the idea of supervised machine learning, where you ask experts to provide examples so that you train machine learning models to mimic the annotation of images. And so in this problem, they were interested to detect these adenocarcinoma tissue regions. And so these images contains a lot of variable tissue like necrosis, inflammatory cells, etc. And so the idea was to ask them to annotate positive example of adenocarcinoma, but also many negative examples. So what we got are training samples of tumors and training examples of non-tumors. And the typical way of dealing with that is to apply machine learning or deep learning approach. At that time, it was in 2014, deep learning was not yet so popular. It became popular then. And so what we use are ensemble of decision trees, which are basically very large structures that performs a lot of pixels comparison. So this is only an illustration of a decision tree, but in practice there are thousands and thousands of comparisons of pixels. And so these trees extract patches in these regions and made pixel comparisons between them and try to identify which of these pixel comparisons are discriminant between the tumor and the non-tumors. And when this model is built, this is a model that is automatically built using the training data. When this model is built, you can then apply it on new images. And so it's basically involved to scan the images. You see the little squares there moving. So we basically, the model, there is a patch sliding over the image, and for each of these patch, the model gives predictions about the fact that the pixels are or not tumors. And so at the end, you get these segmentation maps that hopefully correspond to the detection of tumors. In the field of machine learning and computer science, when we develop this method, we have to evaluate them. So what we generally do with these methods and these data is to see how well these methods are performing compared to ground truth, compared to experts. And so we realized that these methods were performing quite well on these specific data sets. And we also apply these methods on other types of tissues with results that are more or less acceptable by experts. But as I said, we propose a proofreading interface, and so when the experts are not happy with the detections, it's possible on the software to manually proofread and correct, and so the whole process is faster. So the process of combining computer prediction and manual correction is faster than, of course, the fully manual workflow. So that was the first task, segmentation. Another task that we worked on is what is called landmark detection. And so very briefly, in this task, the goal is to detect some anatomy in this type of biomedical images. The goal is to detect anatomical landmarks. And so what we have developed is tools that again need expert annotations. So we have, for example, on this data set, we have about 100 images where the expert manually annotated about 20 interest points. And so we used these images to train models to automatically recognize landmark 1, landmark 2, landmark 3, etc. in several images. And that's the same for the other types of images. And what was important in these studies is to actually use multi-resolution descriptors. So while in the previous task it was possible to predict the texture of the tumors only based on one scale, here it's necessary to take into account the context of the landmark. So these methods basically used not only this little square around the landmark, but we show that we got better results when we also consider larger regions. And so although there is no explicit encoding of the spatial context, by using these larger windows, the methods are able to exploit this spatial context to have better prediction results. So we did not work so this is a paper I actually found two days ago, because I was curious about the fact that would this kind of method be applicable in the field of works of art. And what I found is this one, where they basically use the same kind of method and the same kind of idea of landmark detection, but to study the style of face paintings or even comics, etc. So the idea there is that they apply landmark detection methods to detect some points on the faces, and then they study the organization of these faces, etc., according to different painters. And what they did in this work, which looks a bit funny, is what they use techniques that are called style transfer. So because they did not have a lot of training data to recognize the points in art images, what they did is they start from natural images for which they add landmarks, and they apply some kind of style transformation to try to mimic styles of different paintings. And so with this data augmentation, they show that they obtain better results to detect the face landmarks in art images. The third task is about image or object classification. And so here, this is work done by my colleague Romain Mormont and later by also Mattia Sabatelli. And so Romain worked in the field of biology and Mattia in the field of works of art. And so the idea here is basically to see if the current methods, the current deep learning methods that are available, these methods developed by Facebook, Google, etc. The idea of this study is to assess if we can reuse this architecture of deep network and classify biology images or art images. But what you have to understand is that most of these deep network has been built using ImageNet, which is a very large data set of millions of images, but these are natural images. So in ImageNet you have images of dogs, cats, cars, different types of scenes. And so these very well-known deep learning methods were mostly all built on this data set. And so the idea is to see, can we transfer the model that we have used, that have been built on these natural images for very specific objects in biology and art. And so very briefly, what we have evaluated is this network on different types of biology problems. So like recognizing different types of cells here, or different types of tissues in renal biopsies, etc., etc. And to make the story short, basically, yes, you can use this network that were built on the natural images, and you can use them to classify biology objects. And so if you reuse from this network as they are, you already obtain quite good results. So these are recognition rates, so that means that 90% of the time this network is able to recognize the types of cells, etc. And what we have tried is different strategies, ways to reuse these deep networks. And what we have shown is that, like in other works, you can fine-tune these models, so that it's basically updating the weights of these networks, and so basically fine-tuning the transformation that they are applying to images. And when you do that, you obtain better results in all of the cases, or at least on our data sets. Mattia did reuse the same idea on works of art. So here, Mattia extracted from the Rijksmuseum website 3 data sets. And so he worked on 3 classification tasks. The first one is he wanted to assess if this network can classify materials. So the data that he collected consists in a bit more than 100,000 images. Each of these images has one single label that comes from the metadata of the Rijksmuseum. And so one of these labels are materials, like for example paper, gold, porcelain, etc. And so the goal here was to assess if this network were able to classify the material of these images. The second task is somehow correlated. It's the types of works of art, so like prints, sculpture, drawings, etc. So the data set is roughly the same size. And then the last data set it collected is the artist data set. So he has about 80,000 images, and each of these images has of course one single artist annotation, and so this data set consists in almost 1,200 classes. And so what they did is to evaluate this method is to use some subset of the images to train the models and to fine-tune the models and then to test them in an independent way to assess the performances of these models. And so again, we used different strategies, so basically using the networks as they are without any adaptation. So this is the ImageNet off-the-shelf features, and he also tried to fine-tune these models, and he also tries to train networks from scratch. So this is basically not using at all the ImageNet images, but training the networks from scratch. And so what you have here, to make the story short, is the three classification tasks: materials, types, and epochs. And you have different lines corresponding to different architecture of deep networks, but also what you have here is the orange line, which means, so you can take, for example, the point here, which means that this network built from scratch will reach about 88% of accuracy, so 88% of the time the models correctly predict the material of the image. But you see here is that you can get better results by fine-tuning these models. That's the same conclusion for types, and this one is for artists. So you can in general get better results by fine-tuning these models. But what you also can assess here is that the artist classification is much more difficult than the material and types classification task. This is partly due to the fact that this artist dataset, so we have this number of images, but we have a very high number of classes, and for some of these artists we only had a few examples, and so the network, for the network it was very difficult to train, to recognize these artists because of the very low number of training images. Mattia did an additional test on another collection coming from a museum in Antwerp, and that's the same conclusion. I will not enter into details, but basically fine-tuning these models bring better results, and fine-tuning them using, so this column correspond to, no, this one correspond to fine-tuning the models using both ImageNet images, natural images, and Rijksmuseum images. So that means that if you can exploit images from another museum, let's say, you will get better results. So the one conclusion would be that it would be nice if all these museums can share their images and build very large deep learning models, rather than having each of these museums working in their own restricted circle, I would say. But beyond recognition rates and accuracies, what Mattia started to do is to try to analyze how these models are recognizing the images, which part of the images are contributing to the correct recognition of the images. And so I don't remember exactly the details, and I'm not able to recognize the artist here, but so the task is to recognize the artist. And what you have here is the region. So this column corresponds to the ImageNet models, so the ones that were not fine-tuned. And this one corresponds to the network that were fine-tuned using Rijksmuseum data. And so for all of these three examples, the ImageNet models did not correctly identify the artist, while the Rijksnet models correctly identify the artist. And what Mattia has observed here is that the Rijksnet Museum seems to focus on the people on the lower side of the images, and this seems to be the factors that allows these networks to recognize the artist. While in the ImageNet models they try to recognize the artist, but they were focusing on the buildings, but this was not useful to correctly classify the artist.
So, Raphael, sorry to interrupt you. When you call it ImageNet model, you take the last layer and you do like a SVM on top of it?
Yeah. we have other example of this. So again, is to classify the artist, and so in this case, what was useful for the RxNet network to recognize the artists were these little lines here, and maybe also the lines here, etc. And for these two examples, it looks like it's the face or the shape of the face, or we don't know, but at least that's what the network used to correctly recognize these artists. In this case, the goal was to recognize the material, which is a glass wall of a church, and the network seems to use actually the text in the bottom part to correctly identify, and also this region to correctly identify the material of this image. The last task to illustrate is object detection and recognition. So in the biomedical field, you can use, in some of the applications in the biomedical field, you can use quite simple approach to detect the cells and classify them. So in this type of problems, you can use simple, what we call thresholding approach that detect the objects because there is an uniform background, and so it's easy to distinguish between background and foreground. And so in this field, you can use, I would say, simple methods to detect the object and then classify them. But in natural images and works of art, it's not so easy because there is no uniform background. And so what Mattia did, it's quite preliminary work, but he reused a state-of-the-art approach in deep network to detect objects. And so this method is called YOLO, which generates many, I would say, hypotheses about localization of objects, and then each of these localizations is classified to try to identify the objects. And so Mattia basically reused this architecture from, that were publicly available on some of his data sets. And so, for example, these are examples of results he obtained. So the method correctly detects people or persons or also Apple. So I could stop here and say, okay, it works, but as we are honest people, we will show you a failure of these methods. And so these are, for example, failures. So, okay, the person are correctly detected, but here it detects a dog. Here it's missing persons. Here it detects a cow. And you see, sometimes what you have here is the number. Sometimes these numbers are quite high. I can't read. Oh, this is detected as a dog also. Okay. And these are other examples. So a person are correctly detected, but the musical instruments are not. And that's actually some of the work that they want to do in this InSight project is to detect musical instruments. And so that's a pity that these methods are not working well. And so Mattia will continue this work to try to improve these models to detect the musical instrument. But that brings me also, these failures also motivated me to show you other examples and studies of deep learning failure or vulnerabilities, because there is a lot of enthusiasm about deep learning, etc., and we are also enthusiastic about it because it brings a lot of improvement and progress in the field of computer vision. But just with these two slides, I want to emphasize the fact that these methods are not yet robust enough to be deployed in production, I think. And so, for example, this study done by a group of researchers shows that if you apply this deep network on this kind of image, it correctly detects the persons. But it's possible to fool this deep network so that if you put this little patch on top of this person, then the networks completely fail. And you have other examples here. the person is correctly detected, but then if you put this specific patch, it's not, the method is not detecting the person anymore. And actually there are methods that it's a very hot topic in the field, which the goal is to train adversarial say network to train new models that are able to fool other models. And so you have here other examples in the biomedical field, where you have, for example, here two examples of skin images that are, so this one is normal and this one is malignant. And so the traditional deep networks correctly predict the fact that there is no disease, so 0% of disease and 100% of disease. But it's possible to build methods that will generate very small modification, transformation in the image, so that the methods, the deep networks, then will completely fail. So in this case, it's not even perceptible by human eye that there were modification in the images, but they are, and this very little perturbation in the images makes that the system completely fail. That's the same if you add this kind of modification to the image, it will completely fail and say that it's cancer tissue while it's not. So anyway, what the last three slides I want to present is what is ongoing in our group. So we, in the context of the Insight project, there are art historians and people from museums that are currently annotating a large set of images using cytomine, and they are annotating musical instruments. They want to study the evolution of representation of each instrument in different collections, and so they are annotating these objects manually with the idea to improve the deep network models and to automatically detect these musical instruments in very large collections. And so up to now they have collected, it's not so big, but still I think it's interesting. We have now about more than 2,000 musical instruments that were annotated with the tool. What we are also aiming at is working with other groups that are in fact analyzing images of paintings but with multispectral camera. So we are trying to collaborate with people who acquire very large resolution images of painting, but there is not only the visible images, but thousands of multispectral images, and so that's a new challenge for us because it represents a lot of data to analyze. And maybe it's not exactly works of art, but we have started a collaboration with Stefan Polis here to try to do some papyrus matching, trying to rebuild papyrus using deep networks to detect the similarity between fragments of these papyrus. And so to conclude, I presented you the cytomine software. It's freely available, it's open source, so you can install it in your own institute and work with it. It's not universal, of course, we are not solving everything, but it's fully extensible. And regarding deep learning, it of course, maybe it's a bit very critical here, but I would say that of course it performs very well on many different tasks, but still it has limitations as I showed you, and on our collection the methods were not performing well enough. And so what I believe is that at the moment it's still very important to have the human in the loop, and to, when you collaborate with people developing deep learning methods, I think it's important to ask them to also provide interpretability in the form of, for example, attention map, etc., to better understand how these methods are working. And so personally, I still see these methods are not good enough to apply them without looking at how they are working. So that's why I see them still as companion, as was previously mentioned, of these studies rather than as black box methods. And so I would like to, of course, it was the work of many people since 2010, and so I want to acknowledge these people working at the institute and also the funding agencies that allows this work. And with that,
thank you, Raphael. We saw with Michaela how biology was so important for the study of morphogenesis and art history, and here we see that your first field of research is biology and how we can transfer image analysis to the field of artwork, so it's very interesting and very intriguing. So I guess we can launch a discussion.
Well, it's obvious that your work is very important, it's used by biologists, it's very good, and I think that in some limited cases, applying classification paradigm to art images is useful, but that's not art history. Art history is about ideas. It's not about classifying images or correcting correcting wrong metadata in the database. This is technical things, but not art history. If that's art history, this art history explains why history is the least relevant, least interesting academic discipline today. If that's the limit, so we have to also do something more ambitious, which our historians haven't done before. That's my opinion. Otherwise, nobody's going to care. When people write everyday articles how humanity is dying, yeah, because we don't do interesting things which are relevant to people. Anyway, sorry, but I'm just simply reacting because there are so many computer sciences, right, which apply deep learning for taking this basic classification and then just projecting it out fields. And it generates lots of papers, and sometimes I wonder why.
I agree with you. I'm not directly connected.
So I'm sure you have a good answer. You're just showing examples of that work. Maybe it wasn't you just showing examples.
Yeah, so I'm not directly working.
Okay.
So it was the work of my colleagues, but they are collaborating with art historians.
Yes.
And we found out that it's quite difficult to define questions on which to work on, at least with our collaborators.
Most of historians don't have imagination or ambition to do anything interesting. That's the problem. So sometimes I feel like the computer probably can be better historian than that.
But I think that, for example, the idea of detecting musical instrument and trying to identify the different representation of this instrument over time, etc. That's an interesting art historian study, I think. So we started to try to provide these tools to detect musical instruments by hoping that some art history interesting question will be solved with that. For example, studying the correlation of this instrument, spatial organization of this instrument in the paintings, etc. That might be useful in art history. But we are computer scientists.
Sure.
And we don't have the art history background. But I agree with you that there are many papers that solve problems that are not useful.
I just wanted to know, because you started with cells, right? And I know about cells because I started my own explorations with imagery, so I understand about cells. So I think one of the also limitations of the current paradigm of object detection is ImageNet, right, or clarify, can detect 16,000 types of objects, but we're talking about forms, right? So we're talking about visual rhythms, we're talking about parsing paintings, which are maybe don't have people, like clouds, right? So you can also look at representation of clouds and how clouds are represented in the living painting, which will be relevant to climate change, and so in fact the cells, which are these abstract shapes, can have a particular relevance. And this type of structures can have particular relevance to our history, to be able to write about things we were not able to write before, such as like non-human forms or non-objects. So images are not just paintings of people with still lives. So very interesting connections here. Thank you.
I agree that this is not art history, and art history is about something else, but the question is, do we want to do strict art history here, or do we want to do something that we call visual studies? And visual studies is also about seeing, about human seeing. And I thought most interesting was where ImageNet and other training data fail to recognize something that is easy for us to recognize. And exactly this is the interesting gap where we learn something about how the computer sees and how we humans see and how much of a difference there is. And that in the end can also help art history if we to understand our tools that we're using for systems that we're building.
But visual culture is not, it's about seeing, but it's also about other types of images which are not art images, which we can only sell, sorry, the God punish me for. I'll be quiet.
So, other questions, comments, remarks? It's late, I see. Maybe watching. We have still 5 minutes.
For one question.
For one question. Yes, please.
Small thing. I think there was a classification task that you were taking in the material or authorship. Yeah, we agree that like the accuracy level are not that important. It's much more interesting to look at this like decision map to get a bit more insight what's happening. We drive a bit more information. What about like the errors, like the confusion matrix? Was it anything interesting to look at? Like what was it confusing things with?
I have to say I don't know. It's the work of Mattia, and I don't know if he looked at this confusion matrix. We have many classes, hundreds of classes. So I don't know if it's easy to extract any relevant or interesting.
More qualitative, but like, is it mistaking people from the same family, from the same tribe? Is it does it seem to confuse things which are more like semantic things, like these people that are doing the same kind or the same kind of medium? Is it confusing engravers together? Is it confusing painters together?
This is something that should
still
be.
life painting.
This is indeed something that should be done, but with collaboration of art historian and because from our computer scientist side we don't know which confusion are interesting to analyze. But,
So I think it's now time to close this first day, very stimulating day. And so do we have some practical information for?
We are going to the restaurant tonight.